Hello, physics. I'm going to give you some notes here about simple harmonic motion, which is also sometimes just referred to by the initialism SHM. In case you didn't know the difference between an acronym and an initialism, I'm going to tell you right now because I learned this. I probably said this in some other notes, so you think I'm crazy. Just some old guy who repeats himself. That may be true. But SHM is an initialism because we don't pronounce it. We don't call it shm. We call it SHM. So, for example, the CIA that's an initialism, whereas the FEMA, sorry, that's the one I'm thinking of. FERPA is a thing too. FEMA, the Federal Emergency Management Agency, I think is what that stands for, but that's an acronym because you say it, FEMA. You say it like it's a word. So that's an acronym. If you just say the letters, it's an initialism. All right, so now moving on to the rest of today's lesson. What's simple harmonic motion? The simplest example of simple harmonic motion is a mass on a spring. So if you imagine a mass mounted here, there's no friction here. And this is an ideal spring with spring constant K, where we can imagine the mass just being at rest at the position where the spring is at its equilibrium position. Now, what would happen if you pulled the mass off to the side and then let it go? Well, I have one of the lab carts here, and I attach it to a spring, and this is most certainly not a frictionless surface, and it's not the track that this cart likes to ride on. But there's the equilibrium position for this spring, and if I move the cart off to the side a little bit, you can see that it will oscillate back and forth. And you could have guessed that, right? And you've seen springs before, so if that just kept going like this, like if there was really frictionless, if you're wondering, how did that get to be frictionless all of a sudden? I'm just kind of driving. This is, my hand is just sort of pumping it a little bit from the other side off the screen. So that is simple harmonic motion. Classic example of it, the mass on the spring. So let's see what we know. We know stuff about this, right? We know that in this case, the net force on that block M is just the spring force, because there's no friction, and the normal force and the gravitational force would cancel each other out. Now, sum of all forces is mass times acceleration. And spring force, if this is an ideal spring with spring constant K, is equal to negative Kx. And now, that's all fine and good, but now that we have a good bit of calculus under our belts, we might be tempted to look at this in its differential equation form and rewrite acceleration as the second derivative of position with respect to time, and move this constant to the other side. Like that. And this is sometimes called the signature of simple harmonic motion. And what are we talking about? Like, what's the signature of simple harmonic motion? The signature is the second derivative of position is directly proportional to the opposite of position. That's the signature. And that can take different forms, we'll see, like when we get to looking at pendulums later in this chapter. this doesn't have to just be, it doesn't have to be a mass on a spring, it doesn't have to have a spring constant, but it does, for it to be simple harmonic motion, this has to be true, that the second derivative of position has to be has to be directly proportional to the opposite of position itself. And, you know, there can be some constant of proportionality here, of course. All right. So why is that the signature? What's the big deal? Well, from a calculus point of view, what function has this property that the second derivative of it is equal to some constant. In this case, the constant was k over m, but I want it to be as general as possible. Some constant times the original function. What function or functions have that property? Sine and cosine, right? Because that's just an exclamation point because I'm excited about that, not a factorial, because cosine x factorial doesn't really mean anything. So sine and cosine do. Well, the second derivative of the sine function is negative sine, right? And the second derivative of the cosine function is negative cosine. Those are the functions that have that property. So when we recognize that, we might think, okay, so that means that the position function must be sine or cosine, which makes a whole heck of a lot of sense. I mean, if I just asked you, like, what do you think, what kind of function would model this kind of motion as this thing goes doing, 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 back and forth? Well, it's going back and forth, oscillating like that, and the functions that we probably are immediately going to think of that have that kind of behavior are sine and cosine, right? So that means that the position as a function of time must be equal to, well, let's think about this for a second. As I pull this thing off to the side and let it go, you could use sine or cosine to model this. It all just depends on when you start keeping track of time. But it makes sense to me, and we're going to use most of the time, that at that instant when we're like paying attention and starting the timer, that this thing has been pulled off to the side and we're like, ready, go. So that at time 0, it's at like maximum position. And so which one of the trig functions, sine or cosine, has maximum position at time 0? That would be the cosine function, right? So I'm going to use cosine. I'm going to leave a little room here. Right? And then what is the amplitude of this cosine function? Well, it's whatever the amplitude of the oscillation is, right? Oh, we know how to do that. If you want the cosine function to peak and then also have minimums at that value, a, negative a, negative a, then that just has to go out front. And we can also look here and say, well, in this case, when I took the derivative of this twice, I didn't just get negative x. So I didn't just take the derivative of cosine and get negative sine, then negative cosine. I got this thing, which came out here. So what does that mean must be on the inside of this? There must be something. We're going to call it omega. If you're like, wait, I thought that was angular velocity. This is very much like angular velocity. It's not an accident or some, just because we ran out of letters and we decided to use this one again. We'll talk about that some later. So this thing here, if you take two derivatives, then let's see. Let's go ahead and do that. What would the velocity be? Well, when I take the derivative of this, I'm going to get negative a, the chain rule is going to pop out one of these omegas, sine omega t. And when I do the acceleration, that's going to be negative a, another omega pops out there because of ye old chain rule. And that is the relationship that we're looking for. You can see how that matches up to this. I knew that acceleration was going to equal negative something times x. And there it is. Acceleration is equal to negative something. The something is the omega squared times x, because x is a cosine omega t. A cosine omega t. A cosine omega t. A cosine omega t. So the thing here that popped out is negative omega squared. So this negative omega squared, that must be that negative k over m. So omega, in this case, is for a mass on a spring, is equal to the square root of k over m. Right? Cancel out the negative signs, take the square root. And we know from trig functions, just things that we know since pre-calculus or probably earlier than that, that the period of a trig function which physically, in this case, means the amount of time it would take for this thing to go from its maximum amplitude all the way through one oscillation all the way back to maximum amplitude again. So that's the period of oscillation, right? The time it takes for one cycle through that motion. And period is equal to, for any trig function, it's equal to 2 pi divided by whatever's here, right? You know that from pre-calc. 2 pi over omega. And that, since omega is equal to this, 2 pi divided by that would be 2 pi times the square root of m over k. That is the period of a mass oscillating on a spring. So that is an awful lot of what you need to know. What do you need to be able to do if you're thinking about in terms of other things we've done in recent chapters where like you needed to be able to derive the acceleration of a rolling object. In chapter 13 you needed to be able to derive the velocity of something in circular orbit in Kepler's third law. So like, do you need to do all of this? No, but you do need to be able to do this, to just write out that basic thing. And then from here, this is really more of like an aha moment, because we're not really like doing any calculus here. We're just kind of recognizing, oh, hey, I know a couple of functions, sine and cosine, whose second derivative is just negative of themselves with some multiple coming out because of the chain rule. I know about two functions like that, sine and cosine. So this is just like an aha, and then recognizing that, oh, and the omega squared must be equal to this, right? Omega squared must be equal to whatever is showing up right here, and then doing this. So we'll talk more about that when we do some free response questions eventually. But the College Board likes it when we say, when we write this down for whatever situation, and then we say, by analogy to a mass on a spring, the period is equal to 2 pi divided by omega, and then whatever omega happens to be in our given situation. So you'll see what I mean about different situations when we get to your pendulum notes in not very much time from now. All right, I'm going to just talk at you a little bit more, a couple more minutes, about energy. You know about energy. In this situation, for a mass on spring in particular, and you can generalize this to other simple harmonic motion like a pendulum very easily. For a mass on spring, there are no non-conservative forces. We're assuming that there's no friction, and spring force is a conservative force. So that means that total mechanical energy is conserved. Yeah. And that is a powerful problem-solving tool for us if we recognize this fact. So that means that as the mass oscillates back and forth, between here at x equals 0, here at x equals a, that's its amplitude, and here at x equals negative a, as it oscillates back and forth, what's going on with energy? Here, the mechanical energy is equal to, at this point right here, the velocity would be equal to 0, right, because it's turning around. And here, the velocity is at a maximum as it speeds through the center. Right, as soon as it passes this point, then the spring is going to start slowing it down. It doesn't immediately stop it and like reject it back the other way, but from in between here and here, when it's moving this way, the spring forces this way, and of course if you have velocity and acceleration in opposite directions, that's slowing down, and then it turns around, and now velocity and acceleration are the same direction. Acceleration and force, of course, are the same direction, and so on. So here, the mechanical energy is 1/2 kx squared, but the x is equal to a, so it's all that. Here in the middle, the mechanical energy is equal to 1/2 m v max squared, and here we would be back to mechanical energy is 1/2 k x, but x is negative a squared, so 1/2 ka squared. But all these mechanical energies conserve, so these things are always equal to each other. And at any other point in between, it's a mix of kinetic energy and potential energy, but they always have to equal the same total. So if you know what the maximum velocity is, well, then you know the total mechanical energy. If you know what the amplitude is, well, then you know the total mechanical energy. And then you can find out velocities for points in between and stuff like that. So that means that 1/2 m v max squared is equal to 1/2 k a squared, right? And if you wanted to solve for v max, that's going to be equal to a times, let's see, the 1/2 would cancel out, I would divide that over here, 1/2 times the square root of k over m. And remember that the square root of k over m, that's omega. And then you're like, wait a second. Well, if you look back at what the calculus told us right here, if this is our position function, then velocity is the derivative of that. And of course, what's the maximum of this trig function? Well, it's just this. It's just the amplitude. It's a omega. So that's like, yeah, there's two ways that we got there to the same thing. And of course, a omega is the maximum. You know what the maximum acceleration is? Well, two ways to get it. You can just look here and be like, well, it's a omega squared, right? Or you could look here and say, well, the maximum acceleration is going to be when the position is at a maximum. So that would be ma is equal to negative k times the amplitude, and then you divide the m over. So the maximum amount of acceleration is k over m times a. But k over m is omega squared, so it's all right there. Isn't that cool? So I think that is all I need to tell you at this point about simple harmonic motion. I'm just going to, I have a physics book here, and I remember what problems that I assigned to you, so I'm just going to take a really quick peek at them and make sure that, in fact, I told you everything that you need. I'm pretty sure I did. But I want to be sure. Let's see. So I think I asked you to do 1 through 13 odds. And, oh, I know what I need to tell you. There was something else. And, yeah, okay. So I just want to tell you that this omega is called, in this context, you're like, well, I know it's angular velocity. Here we call it angular frequency. And why are we using the omega? Because consider this. Consider an object in a uniform circular motion. And then with angular velocity of omega. And then consider like the shadow of that, or only like the x coordinate of that. So if you only cared about the x coordinate of that, then when this was here at position 1, and then here at position 2, and then here at position 3, I don't care about the up-down part of this motion. I just care about the sideways part of it here. So if this is UCM, this is simple harmonic motion, and they have like the shadow, if you imagine a very bright light up here shining down on this object in uniform circular motion, casting its shadow on this flat one-dimensional surface here, you can't tell the difference between uniform circular motion and simple harmonic motion if you can only see the one dimension of this. And that's why we use the omega for that. And the last thing that you need to know is that the frequency of something, in general, not its angular frequency, but its frequency. Frequency is like how often something happens. So, for example, what is the period of the Earth going around the Sun? That's about 365 days. What's the frequency of it? It's once per 365 days. That's how often it happens. Number of times per unit of time. So frequency is just equal to 1 over period. It's just another way of saying the same, really the same information. So what's the frequency of the Earth going around the Sun? Once per over 365 days. What's the period? 365 days. They're just the opposite, upside down of each other. And if that's true, then So symbolically, I think on your equation sheet from the College Board, it's going to look like that. They're going to say period is equal to 1 over frequency, and since period is equal to 2 pi over omega, that means frequency is equal to 2 pi. Let me make sure I'm doing this right. 1 over frequency. Hold on a second. I don't want to mess this up for you. I think I'm writing it the wrong way around. I think I'm going to have the omega on this side. Let me just do a little, very quick little bit of cross multiplying and algebra, like, yeah. So what I want to say here is, so omega, let me just cross that out. Omega is equal to 2 pi times frequency. All right. As if you cross multiply those, omega is 2 pi over period, if you just rearrange this. And since frequency and period are upside down of each other, that means omega is also equal to 2 pi times frequency. So when you just, if you see that frequency mentioned there, that's what that is. It's just the period upside down. You can just invert that. And then, of course, what would the units for frequency be? The units for frequency would be, well, the units for period are seconds, the SI units, so frequency would be upside down of that, which would be seconds to the -1, which is fine. You can use that for units, or you can use hertz, which is symbolized or abbreviated HZ. That just means per second. That's what hertz is. So the frequency of our alternating current, when you plug something into the wall, for example, that alternating current is alternating at a frequency of 60 cycles per second, or 60 hertz. Yeah, there you go. So that is all you need to know. Promise.